Okay, let me start. So we are gonna gear back to like basic research again. This is kind of actually compliment Yan this morning about antibody that design using using peptide directed approach. Okay, and we're gonna show a software that can help a researcher produce antibody using that approach. Okay, this work has been done when I worked at the NIH 2 years ago, but it's still increasing more use right now. So just wave your hand if you want to interrupt. So you might never heard about this, but our software is the name is AbDesigner. So why we build this one? So because like in the old day, we used to make antibody ourselves, and then normally when you want to design epitope, then you have to grab several tools, and then try to analyze it separately. And it's not easy as you might if you have never ever tried that. So we want to do something all in one package. So and also it's not open source and it's not interactive. So we build this one, so we call it integrated tool. So it's interactive, open source, and it has some artificial intelligence base to help you design or pick epitope, peptide epitope. So we can now start thinking about making antibody, to the whole proteome, make it faster to facilitate this process. Okay, so that's the goal of our work. So just quickly, show you again the workflow that, when you want to make peptide-directed antibody, then you start with your protein that you want to, make antibody to it. Then, our tool, jump into this step that it helps you look at what region in the protein that likely to make your antibody successful. Okay, and then once you have the peptide, then you immunize to the animal, and then you validate it. So my main focus here is to explain this part of this of this step. Basically, antigen design or selection of the antigen. So if you have a 3D structure, it might help, for some protein that already have a 3D structure, then it might help you, visualize where you would like to have your epitope. But again, this one will work if your downstream application is like ELISA or native, immunohistochemistry. But if you want to make antibody for like Western blotting, then you denature your protein, then this might not work. Okay. Again, antibody, sometimes it's not detecting the linear epitope. It's also detecting the discontinuous, epitope. And then most of the time, then you will try to predict the epitope based on the primary structure. Okay. And our tool is helping, the researcher to try to predict the structure, and then also telling where is a good place to pick the epitope. Like this. Like if you know the structure, then you might not want to pick something like transmembrane region, somewhere that is not easy to access. Then you rather pick the place that's sticking out, more hydrophilics. Again, if you can predict the structure, then again you want to pick something that exposed. Maybe you don't want to select the part that have modification, something like that. So those are the factors around the thinking. So our software, I will do some of the live demonstration, but basically, if you Google AbDesigner, it will pop up at the top, hopefully. Okay, and the interface is very easy. So you just type in your protein name. So right now we have database for human, mouse, rat, C. elegans, most the common one that people like to study. And then when you put it in, then you just I will explain a little bit here. Then you can tell how long all the peptide that you want. And then you can play with the epitope length. Epitope means you have to predict how big of the epitope that really the antibody binding. Once you put that in, then it will give you the it's a Java applet. It's an interactive visualization. So let me show you right now how it looks. So this is the real website. I just put one of my favorite protein, the aquaporin 2, and then this is the output, and you can see it's interactive. You can mouse over it, and I will go through a little bit of this output, so to explain what are these things telling you. Okay. Okay, going back again. Okay, so again, to summarize this just quickly. So this one will grab many information into an easy to view graphical output. So you will see most of the things that show up here will be all the things that most people are concerned about when you try to make antibody. Okay. So it will calculate the immunogenicity score, so that predict how likely that your peptide will sticking out, or more like hydrophilicity. So it's show up here in the green bar here. So the more brighter green, the more immunogenic. So you can kind of spot right away that where is a region that more immunogenic. In this case, you can see C terminal of this. This is the water channel, so it's membrane protein. So it's predict that C terminal and N terminal, the C terminals are more hydrophilic. So it's more clean here. Another very useful feature is tell you the uniqueness of each region along the sequence. So we call it uniqueness score. Okay, so let me demonstrate that. So this yellow one, you can see that basically you can see that the yellow highlight here is highlight the peptide of interest, and down here you can see it show up the multiple alignment. In this case, let's say this peptide, you can see that it has some overlapping sequence with other protein, and this one will show up along the whole sequence. So this is kind of helpful feature, so you can pick the area that would be more unique. And if you have to run this by blast, you don't want to do that. You have to run like 100 times a blast. So this tool allow you to visualize the whole sequence.
Can you easily vary the peptide length window?
Yep, you can. You have to change this one and run again. It take like 15 seconds.
Great, yeah.
Yep. And in this case, let's say I like the green area, at the C terminal here, right? So, and then you can see, is it also overlap with something else also? Okay, and like Jan said, that since this is a short peptide, so look at the sequence itself is helpful in terms of define how unique it is.
You have a custom database in the background, right?
Yes, so we have the database for whole human. So basically, yes, this one is run against the whole species that you input. If you put in mouse, it will search against the whole mouse. Yeah. So this overlapping is defined based on this epitope length, actually. So at this point, I say it has to be exactly 7. I mean, you can do something like BLAST to allow some, similarity, but in this short range, it's faster to compare exact sequence. You can put 5, you can put 4, 5, 6, 7, 8, 9, 10, up to you. You can try, you can play with it. And I think most of the time, epitope length is about 5 to 10, most of the time. Okay, going back here. So what else that is report to you? Uniqueness, okay. Another I think useful feature is conservation. So it's also compare the peptide, let's say human, against, let's say, mouse and rat, or rat. Right now we have mouse, rat, human at this point. Then you can, then let's say if you want to make an antibody that can recognize all species, then you can, or you want to avoid certain species, then that help you also. So like, let's say this one. Like this green region, you can see is conserved, across 3 species, and this is not conserved. Okay. And the rest here, down below here are information that we extract from UniPlot, basically. So, and we make it user, interactive, user easy to use, So you can mouse over, and then it will, tell you what is been annotated in the UniPlot record. In this case, let's say that green area again at the C terminal. You can see that it has some phosphorylation here. Then if you don't like it, then you can avoid it. So in combination, it's align all the information. So you can look at, let's say, one vertical, alignment, and you see, all the parameters that it helps you decide. And if you would have to do this, by hand from different tools, it will take days easily. But this one, you get result within like 15 seconds. Okay. So we'll go through this very quickly since I already show everything. Yep. So those are UniPlot. So whatever is in the record, it will show up.
On the conservation score, what are the parameters that are involved? For example, what if there's a single amino acid switch?
Right now, we just compare exact amino acid, yes.
Okay.
But we think about that also, that we should maybe have some metric.
Oh, I didn't mean to suggest, but yeah. So
no, we thought about that. We thought about that. Just slow down the
But still,
the
you
time.
can look for exact and then make it smaller and then find an exact region. If you're concerned about wiggle or wobble, larger, do that by hand.
Yep, exactly, yeah. So just briefly, very, very quick. So we determine the immunogenicity, based on these 2 famous algorithms, Kai-Doolittle and then Chow-Fastman. This one is hydropathy index, and this one we're looking for something, the turn, the hanging stuff, not the helix or sheet. And uniqueness and conservation, let me show you. This one is, so we use hydropathy and then the turn time together and then get the score. Okay. Here how we calculate the uniqueness and conservation. So let's say you pick a window of 15, and then you select epitope length of 7. So it calculates all possibility, from choice 1 to choice 6, and then it's just compare, So the more overlapping, the more penalty if you get for like uniqueness, or the more score, positive score for conservation, basically. Then you get all the matches. Yep. So just easy pattern matching. I mean, it's basically, I'm biologist, so I'm not looking for complicated, calculation, just easy, like the way that, most of people will look at it. And then we compare with other tools, that are available. And the bottom line is the uniqueness. No other tool, no such tool like that exists. So that by itself is very useful feature. And there are many tools, like it's interactive online, so it's free. And some of the like hydropathy, those are the one that everybody has done that. Okay. And we are right now developing the 3D version. Since the previous version is only for the primary structure, and then we predict from the sequence. And it's under development. So for the 3D, so we kind of calculate the area, it's called solvent accessible area. And then it has more interactive feature that you can select the, on the color, and then it will highlight the location. And we are testing it right now. Okay. So basically, the more area that is sticking off, the more red. And another thing that we're working on is, so we obtain the 3D structure from the crystallography data. So you kind of get also the interacting partner of that protein. So you can use that information to help, let's say you don't want to make antibody within like binding surface interaction, or you may want to make antibody toward that to interrupt the binding, together. So this is under development right now. Okay, so to summarize, so we expect that this tool can help facilitate, the process of design the epitope. So in the future, we can make antibody faster in the design process, though, but validation still takes time. But at least, it's help a smart design of, upstream. So, and yep, I'm happy to take any question.
Have you made any antibodies predicted in
Using this software? Yeah, exactly, yeah. We made like 10, something like that, and about 80% of them work, but it's not easy to say that is it better than not using this tool or not, because it's not easy to have a control. I mean, how you're going to have a control? I mean, it's not easy. So,
but you can certainly say, if it succeeds for you, it's a success. There's no qualification. If you fail, then you don't know.
Yeah. But it's faster for sure. Yeah. It's basically all information are, those are the things that you need to do anyway. This tool just help grabbing it together. So I don't know it's make it better or not, but it's make it faster.
Can you imagine a place? Can you imagine a mechanism of failure? That is a failure to properly load a public resource, or a failure in your algorithm to properly search a publicly available algorithm. That is to say, can you imagine something that might be wrong in your algorithm that could contribute to a failure?
Of course, some of the prediction of hydropathy, those are just prediction, and also those uniplot database. How do you know it's complete? You may have the region that you thought is clean, it's nothing there, but turned out that nobody ever,
Right, but that
identify.
database, that's the database.
Yep,
used
database.
by
Yep,
hand.
yep, yep.
So there's
Yeah.
no, there's no
Yeah.
failure, there's no
Yep.
contributing
Mhm, mhm,
errors
mhm.
by your
Yeah.
program.
Yeah. Right now, I would say we replicate the idea. I mean, the same procedure that most people think about when they make antibody. Just make it.
Yeah.
Yep.
So you're predicting MHC complex binding, is that?
No.
So how does hydrophobicity relate to immunogenicity?
So we thought that, like, if you want to, let's say for native protein, then it's more like it's more exposed. It's more like that. Yeah. And for Western blotting, maybe it doesn't matter. If you fully denature, yeah.
We've got lots of questions.
Mm-hmm.
This software comes from NIH.
Yep.
Or did you design?
Yeah.
Design for them?
I used to work at the NIH.
Right.
Yes.
So what occurred to me was that it falls back on the Swiss prot database rather than its own gene protein database.
You mean NCBI?
NCBI.
I mean, so NIH, we work collaboratively with many people. It doesn't have to be our own database.
But it's not the same. So my next question is, because we know from NCBI it has curated proteins that have been assigned an NP accession code.
The reference sequence. Yep.
Whereas the Swiss prot doesn't have that. Well, it has a symbol to say whether it was verified or not. How does that program distinguish between the two grades?
So we specifically use Uniplot database only, Swiss Pro database only.
But the Swiss prot database has also more disputable types of sequences in there.
At that point, I think we decided to go with Uniplot is because I think WebSeq the data are not that complete, and it's not hand curated. Compared to Uniplot, it's more the quality are better. That's what we thought at that time. Yeah. And then we stick with it.